Okay, this is section 10.1. Just gonna talk about a couple of the graphs examples that show up in this section. You can read through the details of all of these, and I assigned the entire section in the reading. So I just wanted to kind of comment on a few of them and just kind of try to capture the big overall idea with graph models, and that is that the type of graph you use depends on what you're trying to model. So just for the first example here, this is an example of like modeling a national computer network. So here we have, servers in different cities, and the edges here indicate that there is, data can be transferred along some cable or something between those cities. Or perhaps this is wireless, but I'm imagining that this is more of a wired connection. So that's fine, but in reality, if you have a lot of data, for example, that you might want to send between Denver and Chicago, this one cable can only transport so much data. You've got sort of a certain threshold, and so you might want to have a bunch of different connections. So you could take that model and you could, you could make it a little bit more sort of sophisticated. We could say let's make this a little bit of a better model to describe what's really going on here by showing that in fact we have multiple different edges between the same servers at sometimes in order to transmit like lots and lots of data between those servers. Also, you may want servers to be talking to themselves, right? You may want to have what are called diagnostic links, where the server is sending data to itself in order to run checks or that sort of thing. So that can be represented by putting a loop on every server that has one of those diagnostic links. Furthermore, maybe in your graph model you might want to indicate that the data is being transmitted only in one direction and not the other direction. If that's the case, you can use a directed graph to represent that. Right here, we're seeing that data is being transmitted from San Francisco to Denver, but not the other way. Okay, so this would be a one-way communications network. Now, it could be that some of these are two ways and some of them are one way. You see, when they're two ways, you have directed edges going to and from, right, back and forth. You could also use like a mixed graph and have an undirected edge to indicate that there's connections in both directions. And then if you want to, you can sort of combine these together, right? You could say, let's have the directed one-way communications network, but let's also represent how we have multiple different lines of communication between servers where we get a lot of communications traffic. All right. So just as another example of when you might want to talk about, when you might want to sort of adjust how sophisticated your model is, here we have two different graphs that represent calls made between phone numbers. The one on the right is just contains less information than the one on the left, because this is saying these are the calls that were made. These are just undirected edges. Whereas in this graph with the directed edges, now we're also including the information about who called whom. So this graph just contains a little bit more information. If you don't care about who called whom, then you might not care to work with this graph at all, and you'd prefer the undirected graph version. So what type of model you're using really depends on what information you're trying to represent and what information you care to represent for your purposes. Okay. So there's a really cool example here that I think is kind of important given the current pandemic situation. This is an example of an acquaintanceship graph where there's the vertices are people, and then the edges represent that these people know each other. I want to put this in the context of the COVID-19 outbreak. If we think of these edges as indicating that these people interact with each other, then for instance, like the degree of a vertex would represent how much social interaction that person is having. And this whole like connected component of this graph indicates that all of these people, there's links between all of these people. So, for example, if Jan gets sick, then Jan could potentially get Paula sick, who could get Amy sick, who could get Steve sick, who could get Coco sick, right? So having these like paths connecting different people would be sort of a bad thing, like a risk factor. So when we talk about social distancing, you could think of that in the context of a graph model, like this one, where we're trying to decrease the like degree of all of the vertices, eliminate paths connecting vertices, and actually ideally we want to like completely separate yourself and your family so that you form a separate connected component that doesn't have any edge connections to the rest of the graph, which would be like everybody else. So yeah, there's a good deal of like graph. You can really think about this whole like social distancing thing in terms of graphs, which I think is pretty cool. And certainly the mathematics of graph theory is used in studying the spread of disease and kind of trying to figure out how it works and how best to combat it. Okay, I think I wanted to show you one more example. Well, actually, this video is already 6 minutes long, so I was going to talk about the niche overlap graphs in ecology just because I thought it was a neat biology application, but I'll leave that to you. So go ahead and read the other examples. There's a ton of different examples of how you can apply graph theory to model different things. And we'll, I guess, maybe try to talk about those things later.